Hey, what's up guys? And today in this short video, I'll show you how to model the number of daylight hours in Mississauga throughout the year using a sinusoidal function. And yeah, I know it looks hard. I struggled with this too, but we will get through this together. So let's get started. So first of all, we're told that the longest day is in June 21st with 15.4 hours of daylight. That means and the shortest day is December 21st with around 8.9 hours of daylight. And our goal is to create a trig model for daylight hours throughout the year and use it to predict the daylight on February 23rd. And then we compare it with real world data. So the first thing we're going to try to do is find the equation. Since the number of daylight hours varies smoothly and repeat every year, this can be modeled with a sinusoidal function. We'll use the general formula f over fx is equal to a sine bracket k bracket t minus d, where t is equal to time, bracket plus c, where a is the amplitude, and the amplitude in this scenario is basically the change in daylight hours from the average, which is how far the daylight varies above or below the midline. K is basically the period. This determines how quickly the cycle repeats, and in this scenario, this is the daylight hours repeated every day for 365 days. The K adjusts the wave to fit 1 year. Now the D value is basically the horizontal shift or the phase shift. This basically moves the graph left to right so that the maximum daylight hours, which is on June 21st, occurs at the correct time of year. And finally, for the C value, this is basically the vertical shift, or some might call the midline, the average number of daylight hours over the year, halfway between the longest and shortest day. So how do we find these values? Well, first of all, we find the amplitude, since for me it's the easiest one to find. The amplitude is basically A is equal to max minus min over 2. And since with the max and the min is given, with the max being 15.4 and the minimum being 8.9, we use these in the equations, which is 15.4 minus 8.9 over 2, which gets us 3.25. This would be our A value. Step 2, we find the C value, which is the max plus the min over 2. And this will get us 12.15. And I use this one instead of max minus A, which we also sometimes use. I use this one instead since it's more direct. Step 3, we find the period or the K value. Since we know 1 year is equal to 365 days, so the period will be 365. So K, and the formula for K is 2 pi over the period. So basically, K value will be 2 pi over 365. Now for the D value, we'll just use the cosine value since daylight peaks at June 21st or day 172. We'll just use 172 as our D value. And now our final equation will be F over T is equal to 3.25 cosine bracket 2 pi over 365 bracket T minus 172 plus 12.15. This will be our equation, which we will use to predict the daylight on February 23rd. And now our next step is to actually predict the daylight on February 23rd. And since February 23rd is the 54th day of the year, we plug in T is equal to 54. So plugging in the equation will be F over 54 is equal to 3.25 cosine 2 pi over 365 bracket 54 minus 172 plus 12.15. And after calculating all of this, we get around 10.7 hours approximately. So our model predicts about 10.7 hours of daylight on February the 23rd. Now plugging this equation in Desmos, as you can see on the 54th day, which is February 23rd, you can see that the point is on around 10.7, which is like around 10.7 hours in this scenario. So now comparing this to real-time data, and after searching it up with from actual sources such as timeandday.com, Mississauga had around 10 hours and 52 minutes of daylight on February 23rd, 2020. Now, if you're still confused about what we just did, or what the heck did we find, what is the point of all this? Well, basically, to sum it up, we modeled daylight hours using this equation, And using this function or slash data, we predicted like around 10.7 hours of daylight on the 23rd of February. And as previously shown, the real world data showed like around 10.9 hours or so. So our model actually works. This shows that trigonometric functions can actually help understand natural cycles from daylight to tides and temperature.